In this video, I am going to explain force on a current carrying conductor placed in a magnetic field. Here there is a magnetic field acting into the board as shown by this cross mark, and a conductor is there of length L. In this conductor there is a current along this direction, along the positive x-axis. But motion of the electron is opposite. Motion of the electron is opposite to the flow of in the direction of the current. Current is along this positive x-axis. Then direction of the flow of the electron is opposite to that. Then force acting on a charged particle in a magnetic field is given by this relation. It's called known as magnetic Lorentz force. F is equal to Q V vector cross B vector. Our aim is to get the expression for the force experienced by this conductor kept in a magnetic field. First, let us write an expression for force on a single electron. So many electrons are flowing. Then first let us get the force on single electron. So instead of this Q, you can write E. Since the charge of the electron is negative, you would write minus. Then Vd vector cross, instead of velocity, drift velocity of the electron, Vd vector cross B vector. So this is the force acting on single electron. Then you consider a small volume of length dl. So this volume is area of cross section multiplied by length. Then the total number of electrons is capital N. Number of electrons per unit volume, small n. N is equal to capital N by V. So capital N, the number of electrons can be written as N times V. So now we can get the number of electrons in this small element of volume V. Volume of this part is A into dl. Cross-sectional area you multiply by the length, then multiply by the number of electrons per unit volume. We will get the number of electrons in this region. So N is equal to small n A dl. So this is the number of electrons. Then we know the force on one electron. So the force experienced df in this small volume. First we let it get it. N into F. N is the number of electrons and F is the force on one electron. When you multiply, you will get the force experienced by this part. Then for this N, we can write NA dl. NA dl. Then for this F, we can write minus E Vd vector cross B vector. So this is the force on this part. Now there is a relation between current and drift velocity. There is a relation. I is equal to NAE Vd, where N is the number of electrons per unit volume, A is the area of cross section, E charge of the electron, Vd drift velocity. This expression you multiply both sides by dl. Then this can be considered as a vector because this conductor can be kept at a different angle to the field. Now field is acting into the board. Then if it is kept like this 90 degree, it can be kept in different angles, so it can be considered as a vector. Now dl. So here both sides you multiplied by dl. Then this is a Vd vector. So here drift velocity. Here this is current into dl vector, ideal this, and here drift velocity. Current is that side, but drift velocity is along this direction. So drift velocity is a vector. Now since they are in the opposite direction, there is a negative sign. Current is in this direction and drift velocity opposite to the current. That is why here there is a negative sign. So now you can see here NADL EVD, this including this negative sign. we can write ideal. So in this expression df, for this part we can write ideal, then this cross B. So you are getting the force on this small element df, then this entire length L. So instead of this dl we can write L. So force is given by IL vector cross B vector, cross product. Now field is into the board, magnetic field, current that side, drift velocity this side, current that side. Now cross product, try to push with your right hand V to B. B is acting into the board. Now you see thumb is in the upward direction. So force is given by this thumb. So this is the direction of the force. Then when we consider the magnitude, this n cap is not needed. Then we can write F. When we consider the magnitude of the force, we can write F is equal to IBL sine theta. Now let us consider two special cases. Suppose the conductor is kept like this. Field is acting into the board, conductor also in the same direction. So theta will be 0, sine 0, 0. So force will be 0. When theta is 0, force will be 0. Suppose the conductor is kept like this, then field is directed inward, then current that side. So theta is 90 degrees, sine 90 is 1. So F is equal to IBL. So conductor will experience maximum force. Now we have seen, using the cross product, we have seen direction of the force is upwards. Field is acting into the board. Current is that side, current that side. See, now you can use Fleming's left hand rule for getting the direction of the force. Stretch the forefinger, middle finger and thumb of the left hand in mutually perpendicular direction. If forefinger is in the direction of the field, middle finger is in the direction of the current, then thumb will give you the direction of the force. So that is a Fleming's left hand rule. Thank you for watching.